Let's talk about cascading failures. What are cascading failures and how can we prevent that? And how can we design applications to deal with this problem? This problem is really relevant, especially in a world where applications are more integrated to each other, are more connected to each other. Basically, every system, every API is some sort of distributed system. And this is a problem that we need to understand and work on it. So basically the idea of a cascading failure, here we have this diagram over here with three interconnected systems. It's when, for example, we have an unavailability in the system C, for example, and then this failure affects the system B and affects the system A, because system A relies on system B and system B relies on system C. Many times we don't have fallbacks to an implementation, right? So let's suppose we have an application that dispatch emails in part of that application, and we don't have a fallback in case our major email provider is not working at the moment. Sometimes you don't need to have a fallback, and that's okay. But the problem is when that failure related to email will affect other features that we have in that same system. That is exactly the case right here. So probably system A in this diagram is doing more stuff than that feature that relies on system B, and also system B in relation to system C as well. So when our systems start to falling like dominoes, this is really a huge problem. And why this happen and how can we prevent that? So when we think about why the failures propagate, we have the lack of fallback and we have the problem with slow failures. And in today's video, we'll talk about the slow failures because the fallback is just having a second option and implemented that is not that difficult, but it's important to understand why these slow failures are going to cause those cascading failures. So first thing is why failures are slow in the first place, right? Why something is slow only when it fails? So when things are working correctly, okay, the same unit of work, the same type of task that we are doing, it's fast, but it starts hanging and start to getting slow. Why that happened? So when I think about this case right here, we are talking about integration between two different systems. So we are actually hitting an external system and now waiting for that response. We have a network layer on top of that. So the network itself could be a problem, could be slow because we can have a problem in the internet infrastructure, for example, or it could be that system B is facing a problem and not scaling very well or failing to respond. So slow failures are usually associated with the lack of timeouts when we're doing those requests, right? So if you don't have a timeout right here on system A calling system B and system B calling system C, if those systems never respond, we are basically going to lock our thread or CPU or whatever that we are doing in that part. And we can also have the lack of circuit breakers, which is the idea that, okay, if my external dependency is failing, so let's go directly right here. Let's suppose that in the last 5 minutes, all calls to system B failed. If this is failing a lot, maybe it doesn't make sense to continue to put more effort and traffic over there. Would be just smart to just fail that automatically for, I don't know, the next 2 minutes, and then we reevaluate that again. So if in the next 5 minutes, a certain amount of requests failed from system A to system B, we also cut the connection right here. So let's explore those two principles, right? The setting timeouts and actually using circuit breakers and that type of logic to avoid such problems. And those two things right here are related to a single strategy, that is the strategy of failing fast. So failing fast is really important when we think about scalability. So here's the thing. The problem with slowness is the blocking. I will give you two examples right here of applications. So here we have the architecture one, pretty common on APIs. So we have all the incoming requests going through a load balancer. The load balancer then will distribute the traffic among many instances of that API. That API is running into a cluster, so we have a limited amount of CPU cores available for that application. And then we have our external API right here, which the API instances is relying on. And that's external API is really slow, is failing a lot. So what's the problem behind that? And notice that this same problem will occur when you have, for example, a queue and a consumer, right? So we could have a message broker queue right here when we have all the incoming messages being dispatched into that queue, and we have many different consumers getting the message and processing the message from that queue, and those consumers also rely on that external slow API, and we also have a limited amount of cores available for our consumers. So different parts of architecture, different types of a system, but the problem is the same, because this external API, which is slow right here, when we are communicating with that, when we're doing I/O, we'll get stuck. Notice that not all technologies, languages, stacks are going to get stuck when working with I/O. So, for example, Python and Java by default will block all the I/O operations that we do. Ruby, PHP as well, same thing. But we have technologies like Golang, Node, and even Python with gEvent or the async Python library, and Java as well with other alternatives. But notice that in Python and in Java, this is not the default behavior. It's kind of a hack that we need to do. Many of the popular libraries will not be working with non-blocking I/O, so we kind of need to do some hacking to make that thing work properly. It's very different from platforms such Golang and Node that has this principle from the beginning. But notice that even with non-blocking I/O, we are not going to block the CPU, but we still accumulate the tasks, the things that we are working, right? So we still are going to accumulate the memory. So even though from that CPU scalability perspective, we don't have the same issues, like right here, for example, we could like, okay, so core 2 started to do this request to that external API, but it's non-blocking. So while we don't receive the response back from that external API, this core right here could get other message from the queue and process that. We are still accumulating the messages that we need to process. So this is are going to consume a lot of memory, and CPU and memory are not infinite. So this puts a lot of pressure and challenges to scale that, even with horizontal autoscalers. And talking about challenges to scale things, even with autoscalers, why use circuit breakers? Isn't the timeouts enough? So let's compare those two scenarios. Imagine for the same architectures that we saw before. So scenario 1, we have the healthy scenario. So we put like a timeout of 20 seconds. Notice that when we decrease the timeout, we are actually decreasing the probability of making things work, because something could be slow but actually works in the end. So it's kind of complicated to set a timeout, but I put this 20 seconds right here just to have an example. So we have this 20 seconds timeout, and we have this throughput of 1000 requests per minute, and our latency, the P99 latency, is around 2 seconds, right? So the number of API instances that we have to process this amount of requests are 2 API instances. Okay, but then we have a scenario where things start to getting weird, when most of our calls start to fail because we have this slowness problem with this external API. So our timeout of 20 seconds, we have the same amount of throughput, but then our P99 latency goes to 20 seconds. right? Because we have a lot of requests that start to delay a lot and to timeout and everything. So actually the number of API instances that would need to scale that, even with the timeout, would be 20. This is a 10 times the amount of machines that we need to do that. So even though if you have the amount of machines, even though if we could allocate all those database connections and all the challenge that have behind that, we still need to spend a lot of money to scale when we're facing troubles like this one. So it's 10 more CPUs, 10 more memory usage for the same throughput. Also talk about the challenges with autoscalers. Notice that our CPU usage will be probably low because remember, when we are waiting the response from an external system, we are not using CPU at all. So for example, for autoscalers based on CPU usage, we wouldn't be able to scale that, because the CPU usage will be low. So that's another part of the problem why it's challenging to scale applications that are facing those type of issues. This is why implementing a circuit breaker at the same time as we put those timeouts are really efficient to solve those type of problems, because we could detect an external provider, an external partner that are failing, and when we reach that threshold, we just cut the connection, right? And with the analogy right here would be to open the circuit. So every time the circuit's open, okay, so this external partner is failing too often, so we're going to fail that automatically for the next 2 minutes, 3 minutes, whatever. We need to fine-tune the threshold for each specific case, but the principle is the same. If something is failing too much, we then just stop working with that and fail automatically. We shouldn't keep trying to do that and allocating all the resources to something that is not working. And of course, we're doing that for a short period of time, then we recover from that state and we can just forward the requests back to the external platform. And if they recover it, we can start sending requests to them again and things start working again for us as well. But if they are still facing that challenge, open the circuit again and stop sending requests to that again until they recover. So this helps a lot to not be in that position right here, to have to increase 10 times the load to deal with the failing issues. And of course, if everybody implements a circuit breaker, we can help to recover that external partner that is failing as well. Because one of the things that is challenged to recover from an outage, when you have a service that is facing an outage, it's when we try to start up and we receive the huge amount of requests back. So it's a very interesting piece of software that we can connect that. It's just a thin wrapper around the call that we want to have this behavior, and we have an in-memory state that keeps collecting the success, the failures, and the timestamps for that, and decides to open or to close the circuit. This principle is described in this book, Release It. I definitely recommend this book because not only this pattern, but all those principles of failing fast and understand how blocking I/O will be stuck all your CPU, your cores, your threads. It's very well explained in this book. I think it's definitely worth reading it. And that's all for today's video, folks. Have you faced this type of issue in the applications that we maintain? Have you deal with an incident in our organization, in our work, in the software we maintain related to those cascading failures, the lack of timeouts? Feel free to share your ideas in the comment section. Also, if you reach this point, subscribe to the channel and also hitting the thumbs up button. This helps a lot to deliver this video to more people, and thank you.